This week we're going to talk about torques and moments of force. So, specifically changing angular motion and instances in which equilibrium is maintained and how torques change within certain environments. So, objectives that you will have for this chapter are defining torque, static equilibrium, equations for both of these, determining resultants of two or more torques, determining if an object is in static equilibrium, and what forces and torques are acting on that object to make it in a environment of static equilibrium, and then also determining unknown forces or torques acting on an object if we know all other forces and torques acting on that object. We will also discuss center of gravity and how to estimate the location of a center of gravity of an object or one's body. So torque is defined as the turning effect produced by a force. So this is also known as moment of force or simply moment. So torque and moment are going to be one and the same when we are talking about them verbally. So torque causes change in angular motion. For the sake of human movement and exercise, muscles are what create torque about joints. If we use the example of sliding a book on a table as a way to represent torque versus linear translation, we can go through three different scenarios, A, B, and C, in which the force applied is at a different point on the book and in different directions. So in example A, or in scenario A, if we apply a force directly in line with the approximate center of gravity of this book, and in one direction, the book will simply linearly translate or accelerate to the right. However, if we apply a force not directly in line with the book's center of gravity, but with equal magnitude and direction, we can see that in this case, the book does have some linear translation, but there is also a small torque that is produced as well. And in scenario C, if we apply a force at the bottom left-hand corner of the book and the top right-hand corner of the book in opposite directions and of equal magnitude, this will cause a torque alone rotating about the book's center of gravity. There are three main terms that you need to know that are the three main effects of force based on line of action of a force applied. And these will directly correlate with the previous slide scenarios A, B, and C. So a centric force is a force line of action that is directed through the center of gravity and causes changes in translation only. So this would be represented by scenario A in the previous slide, where the book was pushed through the center of gravity and the result was only linear translation. Now the next one is eccentric force, in which the force line of action is not directed through the center of gravity and it causes changes in translation and rotation. So this would be represented by scenario B, in which the center of gravity remained the same, but our force was applied at a different point, and the book resulted in translation and a small amount of rotation. The last one is what's called a force couple, and this is when two eccentric non-collinear forces, meaning they do not have the same line of action but are equal and opposite in direction, this causes changes in rotation only. So this would be scenario C, in which we had the same equal and opposite magnitude of force, but in opposite direction, in which the book caused a rotation only or torque only. A very important component in discussing torques and rotation is a moment arm. So a moment arm is the perpendicular distance between the line of action of a force and a specified axis of rotation. So this is the shortest line between the line of action of a force and an axis of rotation. And a moment arm is represented with the variable r. So moment arms quantify how eccentric a force is, meaning that the longer the moment arm, this increases turning effect of a force. The shorter the moment arm actually decreases the turning effect of a force. So in the case of sliding the book on the table again, if we were to apply a force in the bottom left-hand corner of the book, and we can assume that the center of gravity and the axis of rotation is directly in the center of the book, the distance between this line of action, sorry, that was a bad line, and the axis of rotation would be considered our moment arm or our variable r. Mathematically, we can represent torque as T is equal to F times R, where T is torque, F is the force or the magnitude and the direction, so this has to be plus or minus, positive or negative, in newtons, times the moment arm, which is going to be measured in meters. So the units of torque itself are the Newton meter. So to fully describe a torque that is being applied in a specific scenario, we must specify the axis of rotation and the magnitude of the torque, and most importantly, the direction of the torque. So this can be represented by clockwise in the negative form, counterclockwise in positive, and these you should have, or you should remember from our forces chapter, but these counterclockwise and clockwise positive and negative descriptions are based on our anatomical description that we discussed within that chapter. So in discussing applications of torque, a given size torque can be created based on two different scenarios. So a large force with a short moment arm or a small force and a long moment arm will render the same amount of torque. So if we think about it mathematically, if T equals F times R, and you have a large force and a small moment arm or a small r, and then reversing this scenario, if we have a small force and a large moment arm, T in these two cases should remain relatively the same if the differences in these two scenarios are proportional. So having a great torque doesn't always mean that you have to have a long moment arm. If you have a large force and a short moment arm, you can render the same amount of torque given a smaller force with a longer moment arm. But humans typically use tools to increase torque, most of the time by increasing the moment arm, which makes us have to apply a smaller force. So if you think about trying to remove some type of bolt from something that has a nut that's screwed onto the bolt, if you try to remove it with your fingers, which would be a very short moment arm, you're going to have to use a large amount of force. So a lot of the times what we do is we grab a wrench to increase the moment arm so that we only have to apply a small amount of force to achieve the goal that we are trying to achieve in a certain scenario. In applying torque to our anatomy, muscles produce pulling forces. So we will discuss the force applied by muscles as F sub M here. So every muscle crosses a joint. That's how it is able to produce a torque at this joint. So because every muscle crosses a joint, muscles have moment arms about the joint axis. So the joint axis or the joint center is going to be our axis of rotation. So muscle force creates torque at a joint. And if we think about this or look at this biceps description here relative to its moment arm in flexing the elbow, we have the muscle force of the bicep here. The axis of rotation is going to be the center of the elbow. So the moment arm here is going to be the distance from the attachment of the bicep and the center of the joint, which is going to be our axis of rotation. So when we think about the moment arms of muscles, a lot of times these moment arms are going to be very, very small because our muscle attachments in cases like this are very close to the center of the joint itself. Changing our joint angle can also change our muscle moment arm because the muscle moment arm length varies as a joint rotates. So if we again go with this example of elbow flexion versus extension, our moment arm is actually longer when the elbow is flexed to 90 degrees versus when the elbow is extended. And we can see this depiction here because the line of action of force is what changes in order for this moment arm to decrease. So when our elbow is at 90 degrees, we have the force line of action going through being applied to flex the elbow here. So this is our moment arm length. However, when our arm is extended, the line of action of the bicep now changes due to the length or the lengthening of the muscle. Okay, so even though the attachment site is going to stay the same, the line of pull changes whether our muscles shorten or lengthen. So in this case, it's lengthening. So in order to flex the elbow again, the line of action is going to actually be closer to the axis of rotation, giving us a shorter moment arm here. So strength training torques provide us with a little bit different scenario to think about in that exercise weights create resistance torques at joints. So as a weight is moved through a joint range of motion, resistance torque magnitude actually varies. So weight torque increases as moment arms get longer and decreases as the moment arm gets shorter. So our muscle torque opposes the resistance torque. So we can see here in using a leg extension machine, our moment arm is going to change throughout the movement as the machine itself is providing these resistance forces. So if we think about doing a leg extension in which we go from seated flexion to seated knee extension, the torque provided here, or about the axis of rotation of the knee, is actually a resistance torque. So we are resisting the force that is being applied by this machine. So again, our moment arm does change through a range of motion, as we talked about with the bicep extension. So in this case, the resistance force is actually the stack of weights attached to the machine. The resistance moment arm is the perpendicular distance from the line of action of the cable to the axis of the machine arm, all right? And the resistance torque varies as the machine moves through our range of motion. So that is all we are going to discuss in part 1 of torques and equilibrium. We will get into the equilibrium part of things in part 2, as well as establishing center of gravity and estimating that through different scenarios.